This is lecture 23 of Engineering Physics 1. In this lecture, we continue discussing oscillations. I would like to start by reminding you what we did in lecture 22, very briefly. We looked at oscillations. One of the examples of an oscillation that we discussed was a spring with some object attached to it. And we saw that in this case, if you offset this object by a little bit, you get restorative forces and you will get oscillations back and forth. This motion is described by a simple formula. Your position is a cosine or a sine. This is the basic formula. Since you have cosine, you know that you go back to your original position many times. The meaning of this number is that it's the amplitude. This is the furthest that you get away from the equilibrium. This is your frequency times 2 pi. 2 pi times frequency is this number. And this is just a phase that controls where you start this motion. It's easy to take derivatives and second derivatives of this expression. For the velocity, you will get negative omega a times the sine of the same thing. For the acceleration, you get negative omega squared times a cosine of the same thing. So both your velocity and your acceleration are harmonic. They go up and down. And your velocity could be as high as omega a. This is the highest value of the velocity you can have. And this is the largest value of acceleration that you can have. What we will do in this lecture, in lecture 23, is we will look at other examples of simple harmonic motion. It's not going to be a spring and a mass, it will be something else. But mathematically, all those motions will be equivalent. You will have a formula like this, described by a cosine of time. And then our interpretation will be exactly similar. This term over here will tell you how far you go away from equilibrium. And this term, omega in here, will tell you whether you have high frequency or low frequency. And the only thing that we need to do, since we are familiar with the meaning of this formula, is we have to understand what exactly controls the frequency. For the spring, formula for the period was 2 pi square root of m over k. So frequency was 1 over 2 pi square root of k over m. If you look at this formula tells you that if you have something heavy, it will have high period, so it will move slower in some sense. And if you have a stiff spring, then the period is small, which means that you oscillate faster. Let's start with an angular oscillator, which is something similar, obeying the same equation. The angular oscillator is, I have a picture of it on my slide number 3. So you can imagine some sort of wire suspended, and then at the end of this wire, you have an object. And this wire has some torsion. So basically, if you twist this wire, it will resist the twisting. It will try to get back to its original position. So if you have such a wire, then you will have oscillations because there is an equilibrium, and every time you try to move away from the equilibrium, there is a restorative force. For example, if you have this kind of machinery in the equilibrium, you apply torque, this disc will rotate, but then because of the restorative force, it will move back and it will start oscillating back and forth, like so. If your wire is not a very complicated wire, and if the angle is not a very large angle, then you will have exactly the same equation. You will have a cosine or a sine, some amplitude, and some frequency. In this case, I'm not going to derive these formulas. There are some derivations in the book if you want to look at. I will just write down the formula. So in this case, the period turns out to be 2 pi times square root of I over kappa. I is the moment of inertia, and kappa is so-called torsion coefficient. This torsion coefficient describes how much resistance the wire gives you with respect to twisting. So high torsion coefficients mean that it's not that easy to twist this wire. And if this is your period, then your frequency will be 1 over 2 pi square root of kappa over I, which makes sense. If you have high torsion, then your oscillations will be of high frequency. And if you have high moment of inertia, then your oscillations will be of low frequency, which also makes sense because moment of inertia is basically how hard it is to rotate things. So if this disk is hard to rotate, it will be more difficult for the wire to bring it back to equilibrium. Another simple example of a harmonic motion is a pendulum. We will start with a simple pendulum. In a simple pendulum, you have a string that's suspended, and you have some sort of small point-like object attached to it at the end. This pendulum is at the equilibrium, but if you offset it slightly from the equilibrium like so, then you have this gravity, mg, you have this tension force. They're not completely balanced, so because of gravity, you will have restorative force that will get you back to your equilibrium position. And this pendulum will swing back and forth. The equation is similar. Again, the equation is harmonic, so you will have some amplitude, you will have a cosine, some frequency times time, and the phase. And in this case, I will skip the derivation again because I don't have enough time to derive it properly. But the period turns out to be 2 pi times square root of L over G, where G is gravity, gravitational constant, and L is the length of the wire. And so your frequency is 1 over 2 pi, the square root of G over L. Let's think about this. If you have high G, lots of gravity, then you will have high frequency, so you will move faster back and forth. If you have longer wire, then you have lower frequency, which means that you move slower back and forth. Also kind of makes sense. Now, next level of complication is when you have a pendulum which isn't that simple. So let's say instead of this small mass, you have something more extended, suspended from the ceiling. It could be a rod, for example. or it could be a more complicated shape. But the important thing is that there is this pivot point, and there is gravity. And because there is gravity, if you are in equilibrium, then any motion away from the equilibrium will generate a restorative force, and this restorative force will make you oscillate back and forth. As long as your angle is small, the equation is similar. Again, you have, for your deviation from the equilibrium, you have some number times the cosine of omega t. And in this case, period turns out to be 2 pi square root of I divided by mgh. The frequency is then 1 over 2 pi square root of mgh divided by I. This again makes sense if you are heavier than oscillations of higher frequency. If there is more gravity, oscillations of high frequency. This I is moment of inertia. If you are difficult to rotate, then there will be low frequency. You will be moving slower. And this H term in here is how far away your center of mass is from the pivot point. So this is H. And this basically tells you that if your center of mass is lower, then the frequency will be higher. So this is the formula. Let's circle it. And this formula actually also applies to a simple pendulum that we described one slide ago. And to see how, let's draw this simple pendulum where you have a rope and you have this point-like mass. And let's see what we get if we apply this formula to the period of the simple pendulum. So for the simple pendulum, this formula turns into twice pi times the square root of moment of inertia divided by mgh. In this case, all of your mass is here. So h is basically the length of this pendulum. So let me write L in here, mgl. And for a point mass, we know that the moment of inertia is mass times distance squared. So mass, distance is L, L squared. Mass cancels out, one set of L's cancels out, and we get the period of simple pendulum to be equal to 2 pi times the square root of L divided by G, which matches the formula that we had before. So just to summarize all of this, what we are doing now is we're looking at all sorts of harmonic motions where things go back and forth from the equilibrium. So far, we looked at a spring with the mass attached to it. We looked at angular pendulums where you have torsion that makes you rotate. We looked at simple pendulums, and we looked at extended pendulums. And in all these cases, we had a simple harmonic motion, meaning that our equation for the deviation was amplitude times cosine of angular frequency times time, plus a phase. The only difference is what kind of frequency you get. For the spring, you have square root of k over m. For the angular oscillator, you have a square root of I, kappa over I. For the simple pendulum, you have a square root of G over L. And for this extended pendulum, realistic pendulum, you have the square root of mgh over I. In your homework, you have a bunch of problems with all sorts of pendulums. This is the key equation, and then you have velocity and acceleration, and you just have to figure out what to put as a frequency in here. So this is the end of theoretical section. What I will do is, in the second half, is I will go over a few problems and I will solve them. Since this is an exam week, what I will do is, to make your life easier, I will just discuss some of the homework problems. And then towards the end, we'll also very briefly look at damped oscillations and forced oscillations. The oscillations that we have considered so far were so-called ideal oscillations, where you have this oscillation that goes on forever. But we know that in real life, energy is always lost. So your oscillators, this pendulum will slow down and eventually it will stop, unless there is an external force that's driving its oscillations. And so we will look at how this damping and external force modify this equation right here.